Hello students, this is Vishwajeet Poddar, chemistry faculty from NEET, Altedemy, chemistry faculty, NEET, Altedemy. Before I proceed further, I would like to know about the quality of broadcast. How do you feel on the scale of 1 to 10? You can give us a proper rating. How do you feel about your classes? Secondly, we would also like to know about the state of preparation of your examination. How are you feeling about the state of your preparation? Are you feeling okay? You can choose to press a button from 1 to 3 and can let us know that you are happy with your state of preparation. Okay. This is Vishwajeet Poddar. I am a chemistry NEET faculty with Altedemy. Prior to my stay with Altedemy, I have taught in many organizations. In fact, currently also I am doing that. And I am based at Delhi. I have helped thousands of students to clear their NEET as well as JEE examination. And I am with you to help you guys to clear your NEET examination. Stay with us. The topic that I have chosen today is colligative properties. We will be discussing about colligative properties in detail. Let us move ahead. But are you ready with Altedemy to understand what is colligative properties? Okay, if you are ready, we can move ahead. Well, you will find these slides, study friendly. I have tried to use different colors also. I've tried to make it as interactive as possible. And whatever basically I am trying to say, want to say, you will be finding it in the written format also. So you can choose to follow it carefully and can do the necessary thing. The physical and chemical properties of aqueous solutions containing solutes in general depends on the nature and also on the structure of solutes. Basically, at the outset, we should know that colligative properties are those properties which are dependent upon number of particles. Colligative properties are those properties which are dependent upon number of particles. CP we say. It is dependent upon number of particles. Right? So everything that basically we want to say, you will find it written out here. So there are some properties which depend on number of solute particles. We are always talking about a solution, and this is basically a liquid solution. Many properties are there, physical and chemical properties, which are dependent upon number of solute particles. And it is not depending upon the nature of these particles. So such properties which are dependent upon the number of particles are called as colligative properties. Okay. There are 4 colligative properties. First, we call this as relative lowering of vapor pressure, RLOVP in short. Second colligative property, we call this as depression in freezing point. This is the second colligative property. The third property we call is as elevation in boiling point. And fourth colligative property, we call this as osmotic pressure. This is OP. First, we should come to relative lowering of vapor pressure. Look, suppose we are taking a liquid here. We are taking any liquid, we can take any liquid. It can be water too. And suppose it is in a closed container. First condition is it should be in a closed container. Secondly, its temperature is fixed. Temperature is fixed. We are not changing any temperature. Now, these liquid particles, that is the particles that are here, it will go into vapor. Then again it will be colliding with the walls of the particles. Then it will be coming down. That is to say, the process of evaporation and the process of condensation, it will keep on taking place. And after some time, it will come to equilibrium. And at equilibrium, if we will be measuring the pressure here, that will be called as vapor pressure. When we mix up any non-volatile solute into this liquid, its vapor pressure nu, that is 2, it will be less than vapor pressure 1 that was originally taken. Whenever we will be dissolving a non-volatile solute, there will be lowering of vapor pressure. We try to measure this relative lowering of vapor pressure, and what we generally understand, if P naught is the vapor pressure of pure solvent, we are saying P naught, vapor pressure of pure solvent, and X1 and X2 are mole fraction. X1 is mole fraction of solvent, X2 is mole fraction of solute. Then P, that is vapor pressure of solution, or we can say PS is equal to P naught into X1, right? P naught into X1. Let us now come to see to it. As far as the relative lowering of vapor pressure is concerned, we can also deal or define with relative lowering of vapor pressure in this fashion. We can say like this: relative lowering of vapor pressure is equal to mole fraction of solute. We say like this. It can be understood this way also, like according to Rod's law we have studied. Rod's law. According to Rod's law, PS is equal to P naught A XA plus P naught B XB. This Rod's law is applicable for two miscible liquids. I have written these two miscible liquid. Let us suppose A is solute and B is solvent. Now when we are putting solute, obviously it is a non-volatile solute, then we can write down PS is equal to P naught B into XB, because in this situation P naught A will be equal to 0. A non-volatile solute will not be having any kind of vapor pressure. So if it will not be having any kind of vapor pressure, then we can talk about this. And obviously we can then elaborate this particular reaction. Like we can write it PS upon P naught B is equal to XB. We can also do it 1 minus PS upon P naught B is equal to 1 minus XB. And we can write P naught B minus PS is equal to XA. Look here, we have reached to the conclusion. This expression, the numerator expression in numerator is called as a lowering of vapor pressure, and this entire expression is called as relative lowering of vapor pressure, which is coming to be equal to mole fraction of solute. Basically, by relative lowering of vapor pressure, we want to explain this, right? Relative lowering of vapor pressure is equal to mole fraction of solute. This has been explained here also. Delta P is equal to P naught X2 and other things have been done. But as I have explained, you can follow this. The expression for relative lowering of vapor pressure has been derived from this particular expression, which is used for two miscible liquids. Okay, we can move ahead and can try to understand what basically are we doing. Look here, there is another expression. If you remember, we have written like P naught minus PS upon P naught is equal to mole fraction of solute. Mole fraction of solute means what? Mole fraction of solute means number of mole of solute upon number of mole of solute plus number of mole of solvent. Right? We can do like this. Now, let us do like this. P naught upon P naught minus PS is equal to number of mole of solute upon number of mole of solute is plus number of mole of solvent upon number of mole of solute. This basically giving us 1. Take 1 on the left hand side. We can write like this: P naught upon P naught minus PS minus 1 is equal to number of mole of solvent upon number of mole of solute. We can write down the expression as P naught minus PS and then P naught minus P naught plus PS, which obviously is cancelled, and then taking numerator to denominator, denominator to numerator, we get the expression P naught minus PS upon PS is equal to number of mole of solute upon number of mole of solvent. This is practically a very relevant expression for relative lowering of vapor pressure. Instead of using the previous one, in most of the cases, if we will be using this, our questions, we will be in a position to solve our questions much more effectively, because you do not have very complicated calculations. The second colligative property, we call this as, hello Vaishnavi, good evening, hello Malini. Okay, expression is not visible. I'm trying to write down to the best of my efforts and all those things. I'll try to see that the expression becomes very clear, but I can choose to show you, Malini, that these expressions, somehow or other this pen is not working very properly, but then you can understand I am speaking also at the same time. Try doing it. I'll see to it that I do a better kind of thing. Okay, second thing that we are talking about is called as depression in freezing point. We are writing about depression in freezing point, DIFP, right? In short, we write as depression in freezing point. Look here, the three things that we are talking. What is that three thing? Suppose we have a container and we have a liquid here, right? You mix up some non-volatile solute into it. It is just a question of mixing some non-volatile solute. The three things will happen simultaneously. There will be relative lowering of vapor pressure. Since its vapor pressure has lowered, obviously boiling point will increase, and it is then known as elevation in boiling point. Boiling point for a liquid is the temperature at which the vapor pressure of the liquid becomes equal to atmospheric pressure. I hope you know that. So if we are putting some non-volatile solute into it, there will be relative lowering of vapor pressure, there will be elevation in the boiling point, and third thing is there is depression in freezing point. All these three things happen simultaneously. Freezing point of a substance is the temperature at which the solid and the liquid forms of the liquid are in equilibrium with each other. The solid and liquid forms of substance have the same vapor pressure, e.g. ice and water at 100 degrees centigrade. If you are putting something like, if you are putting ice at 0 degrees centigrade, there will be some content of water into it and they will come to equilibrium, and there will be a depression in freezing point if it is done with a solution. I have explained this depression in freezing point with an example. Not with an example, rather with a graph. You should try to understand this graph. What is happening? Look here. In this y-axis, we have taken vapor pressure. And on the x-axis, we have taken temperature. Now, take a pure solvent, and pure solvent is this. A line is for liquid solvent. Fine. Let us understand B is the point which is the freezing point of this liquid. B is the temperature at which the liquid is, getting frozen. Now, in this solvent, we are adding some kind of non-volatile solute. Now it becomes a solution. Now the graph of this solution will be like this graph D. Whatever was the freezing point previously, it will go further down and it will come to this place, TF. And this particular difference, TF minus T delta F, this is called as depression in freezing point, right? Whenever we are adding a non-volatile solute to a solvent, there will be depression in freezing point, and depression in freezing point means it will go lower. Suppose you have taken water. Water freezes at 0 degrees centigrade. Suppose you put some NaCl into it. Now it will freeze at minus 10 degrees centigrade, let us say. This is called as lowering of vapor, depression in freezing point. Coming to another aspect of it. On cooling, the vapor pressure of the liquid solvent decreases along the curve AB. At B, the solid starts appearing. This is the same explanation that we have done with this entire graphical understanding, right? We are doing the depression in freezing point, and you should understand that how the freezing point of a particular liquid is depressed when we add a non-volatile solute to it. Okay. Now we have given depression in freezing point an expression. We call this as delta TF is equal to KF into M. This is the expression. As I have mentioned it here also. Delta TF stands for what? Lowering of freezing point. And lowering of freezing point will be same if we take in Kelvin scale or in Celsius scale. Suppose somewhere it is written delta TF is equal to 5 degrees centigrade. You should not be you should not be doing like, if it has been given in degree centigrade, then delta TF should be equal to 278 Kelvin. You should not be doing like this. This is a common mistake that students are doing, what I have noted. I will elaborate it with an example. Suppose originally the freezing point was 10 degrees centigrade. Let us assume for a particular liquid, the original freezing point was 10 degrees centigrade. Now it is freezing at 5 degrees centigrade, right? In Kelvin terms, what will you write? It is equivalent to 278 Kelvin and it is equivalent to 283 Kelvin. Am I right? Now, delta TF in degree centigrade will be 5 degrees centigrade. Delta TF in Kelvin is again 5 Kelvin. So if it is a change, delta TF has been written, you have not to convert it into Kelvin scale. Remember it. Otherwise you will be committing blunder. Got the point? Coming to next slide. Kf is a constant known as molar depression constant or cryoscopic constant. Delta TF is called as, molar depression constant or cryoscopic constant. This is the term that we are using. And it is given as delta TF is equal to Kf into M. M is the molality of the solution and the expression that goes like in detail, delta TF is equal to Kf into, how do we express molality? Small w we write weight of solute upon molar mass of solute into 1000 upon weight of solvent. So the complete expression is like this. Delta TF is equal to Kf W upon capital M into 1000 upon capital W. This is how we express the depression in freezing point, right? Okay. We have given this symbolization as delta TF Kf upon W upon M 1000 upon W, or it is expressed like this. Correct? Okay. Yes, there is again a very important relationship that we need to understand. At times it is asked. There is a method to find out Kf also on the basis of latent heat of fusion. Latent heat of fusion. Suppose T0 is the freezing point and delta HF is the molar heat of freezing. And latent heat of fusion and molar heat of freezing, it is related with this expression, and either you can write down this R T0 square 1000 into LF. Sometimes in the question latent heat of fusion is given, LF has been given, and sometimes in the question molar heat of freezing has been given. So these two are one and the same expression. If you put at the place of LF delta HF upon M1, you get the same expression. So latent heat of fusion and molar heat of fusion, both the things can be chosen to express this. It has again been elaborated. Latent heat of fusion per mole of the solvent, LF. M1 is the molecular mass of the solvent, and like this. Coming to another aspect of colligative property, and that we call this as elevation of boiling point. Elevation in boiling point. As I told you, when we are adding a non-volatile solute to a solvent, on one hand there is a relative lowering of vapor pressure. On the other hand, we are having elevation in boiling point. On the other hand, we are having depression of freezing point. So the boiling point of a liquid is the temperature at which the vapor pressure of the liquid becomes equal to the atmospheric pressure. The boiling point of a solution containing non-volatile solute is always greater than that of the pure solvent. And we can understand it by an example. We are taking a container again, putting water here, H2O. We know that freezing point is 0 degrees centigrade. Boiling point for water is 100 degrees centigrade. Now put some amount of non-volatile solute, that is NaCl. Now, the new freezing point will be somewhere around minus 5 degrees centigrade. The new boiling point will be somewhere around 110 degrees centigrade. There will be elevation in boiling point, there will be depression in freezing point. I hope you are getting me, right? We have tried to elaborate it with an example, though the diagram is not very clear as I wanted to, but then you can understand if you concentrate a little bit. It is just an extension of the diagram that we have drawn for depression in freezing point. Suppose this line A is the line for the solvent. Line A is the line for solvent, and if we heat it, it will be reaching to a particular point, that is X, at which the vapor pressure of the liquid will become equal to 1 atmospheric pressure. This will be called as the boiling point of the liquid. And you should know boiling point should be defined in this fashion only. When the vapor pressure of the liquid becomes equal to atmospheric pressure, that is called as boiling point. So we have reached to the boiling point at this point. Now, we are adding some non-volatile solute to the solvent. Now it has become a solution, and we start observing its vapor pressure, and we find that this is the line. This is line CD. Now it will be moving by this path, and we will notice that it will come to, the vapor pressure will come at a slightly higher temperature, and the difference in the temperature will be called as delta TB, elevation in boiling point. Again, delta TB is expressed as KB into M. And the second expression that we have written, delta TB is equal to KB W2 by M2 into 1000 upon W1. Notations are as usual. This entire expression has been written for molality, the way we define molality. Here again we have EIBP constant. This KB is called as EI. Hello Priya, good evening. I hope you are getting me, Priya, right? Good evening. So we are trying to connect KB. KB is also called as, it's called as ebullioscopic constant, right? We have two different kind of this constant. KB is called as ebullioscopic constant. Ebullioscopic. KF is called as cryoscopic constant. Cryoscopic. Or you can say EB is EIBP constant and KF is DIFP constant. If that appears to be more logical to you, you can connect it. Otherwise, in exam somewhere they talk about ebullioscopic and cryoscopic constant, and it is again related to the latent heat of vaporization and delta HF. Again, the same relationship holds as we had discussed. So that is all about elevation in boiling point, depression in freezing point, relative lowering of vapor pressure. These three colligative properties are connected with each other. And why they are connected with each other? Whenever we are adding some kind of non-volatile solute in a solvent, in a pure solvent, its vapor pressure is lowered, and everything is connected to vapor pressure. You need to understand what is vapor pressure. Coming to another aspect, which is called as osmotic pressure. Osmotic pressure. You better know what is osmosis. When a dilute solution of a solute is separated from its solvent by a semi-permeable membrane, the solvent flows into the solution through the membrane slowly. Such a phenomena also occurs when two solutions of the same solute with different concentrations are separated by a semi-permeable membrane. I will give you a very commonplace example. Have you seen resin? Resin is basically, we call this kishmish in Hindi. Good evening, Ali Anuri. Very good evening. Resin. Suppose we are taking resin. आप लोगों को कभी कभी ये चीजें खिलाई गई होंगी घर पे, है ना, किशमिश भिगो करके. So we are taking resin, we are taking water, and we allow it overnight. We allow it to stay overnight. Resin kept in water, right? Here it is resin kept in water. What do you generally feel, or what do you generally find, that after a passage of time, this resin swells, and we find that the water particles have gone inside. This is typically a case of osmosis. Look what has happened. Inside the resin, there is highly concentrated solution. Highly concentrated solution. And outside, we have solvent particles. Solvent particles. And what ultimately has happened? There is a net inflow of solvent particles from lower concentration to higher concentration. In osmosis, there is always a flow of solvent particles from lower concentration of solution to higher concentration of solution. And at times it is also written in osmosis, there is a net inflow of solvent particles from higher concentration of solvent to lower concentration of solvent. Higher concentration of solvent to lower concentration of solvent. We can also understand it like this. The membrane which allows only the molecules of solvent to pass through it, but not the solute molecules, is called a semi-permeable membrane. In short, we call this as SPM, semi-permeable membrane. If two liquids are separated by a semi-permeable membrane, this phenomena will happen. Parchment paper, cellophane paper, some animal membranes, and inorganic precipitate membranes are commonly used as semi-permeable membranes. Now the technology has become very high. We are preparing very high quality semi-permeable membranes. The hydrostatic pressure developed on the diluted aqueous solution at equilibrium state due to inflow of water when the solution is separated from the water by a semi-permeable membrane is called osmotic pressure. And osmosis is also called as endoosmosis because of the inflow of solvent molecules. This is also at times understood, or it is said. Now, osmotic pressure has been found to depend on the concentration of the solution, inflow of solvent molecules, and the molar mass of the solute can be calculated from the experimental determination of osmotic pressure. We write it like this: osmotic pressure is equal to W by mRT, and we also call this as CRT. This is the concentration, R into T. Osmotic pressure method is used for determining molecular masses of proteins, polymers, and other macromolecules. It is a very important statement. It is used for determining molecular mass of proteins, polymers, and other macromolecules. Solutions having same osmotic pressure at a given temperature are called isotonic solutions. Two different solutions having the same osmotic pressure is called as isotonic solutions. No osmosis occurs when such solutions are separated. No osmosis occurs when such solutions are separated. For isotonic solutions, there is no osmosis. Osmotic pressure is associated with the fluid inside the blood cell is equivalent to that of 0.9% W by V sodium chloride solution called normal saline solution. Osmotic pressure associated with the fluid inside the blood cell is equivalent to that of 0.9% W by V sodium chloride solution called the normal saline solution. Now, if we place cells, which cells? Blood cells, in a solution containing more than 0.9% W by V sodium chloride, here it is 0.9%. These are blood cell, right? And let us suppose we are putting 1% NaCl solution. What will happen? This is lower concentration, this is higher concentration. Water will flow out of this cell. Water will flow out of this cell. And cells would shrink. The blood cells would shrink. Such a solution is called hypertonic. I mean, this is called as hypertonic solution. Hypertonic solution. Hypertonic solution. Coming to another aspect of our thing. Hypertonic solutions have higher concentration and possess greater osmotic pressure. If the salt concentration is less than 0.9%, the solution is called hypotonic. So this is being made keeping in view the blood cells, which has got 0.9% W by V concentration. 0.9% W by V concentration. If we will be putting this particular cell in more than 0.9, more than 0.9, what will happen? The flow will be in this direction. If we'll be putting less than 0.9, solution is less than 0.9, suppose we are taking a solution, then the flow will be from this side to this side. Considering 1m glucose solution and 2m glucose solution, it is being elaborated with another example. Considering 1m glucose solution and 2m glucose, let us take a container like this. It is separated by a SPM, semi-permeable membrane. Here we have 1m glucose solution, here we have 2m glucose solution. 1m glucose solution is hypotonic, this is hypotonic, and this is called as hypertonic, right? Hypotonic and hypertonic. If osmosis has to happen, solvent particles will start moving from this place to this place in this direction, right? Okay. What are the application of osmosis? Plants take up water from the soil through the phenomena of osmosis through root hairs. A raw mango placed in concentrated salt solution loses water due to osmosis, which we call as pickling of mango. You must have seen in your house, if some of you must have seen, in villages generally what will happen, that we prepare mango pickle. Before making mango pickle, what we do, we cut mango and put it in a salt solution, high concentrated salt solution. What generally happens, we are putting in a higher concentrated solution. Whatever water particles are present inside the mango, it goes out and it becomes, it loses water and the pickling of mango takes place. It becomes slightly, it's not very smooth, it becomes slightly rough. If the osmotic pressure of the contents of the living cell is not equal to that of content. So yes, Malini, I think you must have seen the process of making pickles. Pickles appear very tasty, but its method of preparation, it involves a phenomena of osmosis. That's very good. If the osmotic pressure of the contents of the living cell is not equal to that of the contents surrounding it outside, two phenomena takes place. One is called as hemolysis, another is called as plasmolysis. We can choose to skip also hemolysis and plasmolysis, but then we know it. Hemolysis is a process of entering of contents into the cell. Hemolysis. The cell bulges and finally bursts. Hemolysis is this process to this process. What is happening? Entering of contents into the cell. Cell starts bulging. It is hemolysis. Plasmolysis is a process of losing content from this big size to this big size. This is called as plasmolysis. In short, you can remember it like this: hemolysis and plasmolysis. Yes, we have yet another phenomena which is also called as reverse osmosis. Suppose, again, we take a container and it is separated by SPM. Here we have 1m solution, here we have 2m solution. Let us suppose. Obviously, it will start moving, solvent particles will start moving from this direction to this direction. And it will flow until the pressure on both the sides become equal. And if you apply a pressure on this side greater than osmotic pressure, if you apply a pressure on the higher concentration side more than what is osmotic pressure, what will happen? A reverse phenomena will start occurring. Liquid will start flowing in the opposite direction, from this direction to this direction. This is called as reverse osmosis. If pressure higher than the osmotic pressure is applied to the solution side, higher concentration solution side, solvent will flow out of the solution. This process is called reverse osmosis. And reverse osmosis is used in desalination of sea. In this context, I should tell you a story. There was a very rich person. He was stinking rich. So what he did, he said that I should stay in an island. So he purchased an island. And when he purchased an island and shifted out there, what he basically noticed that water everywhere, but not a single drop to drink. There was no potable water, no drinkable water. Now he had purchased everything, but he had no water to drink. How to survive then? Then he thought, water is present everywhere. Isn't it there? Can't there be a method through which we can, desalinate these seawater so that it becomes potable? He again spent a lot of money and, he caught hold of a scientist and he said, we have a project that you have to purify this seawater by any means. And scientist has got a job, great job, because there was no dearth of any payment. And he discovered the process of reverse osmosis. And today, you also must be having the RO system of water inside your house. Almost in every house, we have a RO water. RO water is again working on the same phenomena. When you let water undergo reverse osmosis, you won't get anything excepting H2O. You will be surprised to know that in countries like China and Taiwan, there are other countries also, they are preparing potable water or drinkable water from urine even, because of the phenomena of reverse osmosis. Reverse osmosis phenomena is such a great phenomena that even the urine can be purified to make it bottled drinking water. And do not think or do not be under the impression that there will be anything or any trace of any kind of urine. No, nothing. When a liquid or a solution undergoes reverse osmosis type of thing, there is nothing that is remaining excepting H2O. It takes out only H2O, rest of the things are left behind, right? So deliberately what happens when we have RO system inside our house, we deliberately mix up some other salts to make it tasty, right? So that is the importance of reverse osmosis. Well, these are some of the things. There's a want of theory of dilute solution based on experimental results of osmosis, want of proposed theory of dilute solutions, and a non-volatile solute in a dilute solution behaves like a gas. A non-volatile solute in a dilute solution behaves like a gas. Hence, want to propose that all gas laws are applicable to dilute solutions. All gas laws are applicable to dilute solutions. This is the want of law. And at constant temperature, the osmotic pressure of a dilute solution is directly proportional to the concentration of the solution, and he gave this expression: I is equal to CRE, and it is in accordance with the Van 't Hoff's equation. Well, again we have elaborated it. Pi is equal to CRT, pi is equal to N by V RT, and the expression has been made for osmotic pressure. Is once again the repetition of the things. Thank you very much for being with us. I think that brings an end to our discussion on colligative properties. We need to talk to you about Altedemy because regularly Altedemy is bringing one or the other very relevant lessons as far as your subject matter physics, chemistry and mathematics is concerned, and therefore we will request you to join our telegram channel of Altedemy. You can have these watermark there to scan it and get it connected to our telegram channel. What basically will you be getting through our telegram channel is the PDF materials, free classes, announcement, discounts and prizes. Then again, moving to that, you need to subscribe us to get these classes regularly, free classes regularly. If you have joined us, that's very good. But then if you have not joined us, we would like to tell you about our courses. We have 90 plus classes, more than 100 classes. It's a convenient educational platform, very convenient educational platform. You will enjoy learning here as you are doing right now. The syllabus that has been prescribed by NEET experts, we have flipped classroom method, doubt solving practice, and likewise things. How our class look like? Joining our class, you should understand it will be a privilege for you. Altedemy is doing its best to make you successful. Whatever best that can be done, it is being done. Our classes look like we give you theory on one hand. We give you study material also on the other hand. We conduct webinar regularly as we are conducting it right now. We give you homework, plenty of homework, and those homework is checked. And then you understand where actually do you stand. We have built up our program into different methods, and we call our program as light program, smart program and proficient program. The features of light program are: we have interactive live classes, we have structured courses and PDF, we have live tests, and we have physical notes. These are something we provide. Our smart course, which is our most important and carefully built process, here you get all those four things that I mentioned, that is interactive live classes, structured courses and PDF, live tests and physical notes. And besides that, you get three more important things. That is one-to-one mentorship. Secondly, you get live doubt solving. You can do it. You can get it done. You get mock tests regularly. You find all those things. And then we have a proficient program here also, where we have all those features that we have discussed, Along with that, we have additional support for those who think that they have completed their syllabus and they want to move ahead with higher concept. Then that will be a one-to-one situation, and then we will be dealing with that separately. Look here. Normally, our course stands for 3299, but as a part of our promotional program, we are offering you this course for just 299 rupees, and you will have to use my promo code, that is NEET CHEM 30. If you plan to join, you can choose to give this code NEET CHEM 30, so that you will be benefited and you can get this entire benefit in just 299 rupees. Come on, we are asking for just 299 rupees, and we also understand that it is peanuts for you. Try, take a chance. Thank you very much. See you soon. That brings an end to our lesson for, you know, colligative properties. I hope you must have learned certain things, understood certain things, and will try to use it for your examination. Thank you very much. Thank you all. We bring an end to this session. Thank you, Vaishnavi. Thank you, Malini. Thank you, Priya. Thank you, Alia. Thank you very much for being with us. Keep track of us. We keep on bringing a lot of good such lessons to you, and I hope you will enjoy it. Thank you.